Okay, I'm back. I'm back. Why don't we start taking a look at Maclaurin's theorem and Maclaurin series expansion? I'd actually done this video already. I'm ranting at myself, but I did it without audio on, so I have to do it over. Anyway, here we go. Many functions can be expanded as a series of ascending powers of x. The series of ascending powers of x is also called a power series or a polynomial series. And note the series expansion is usually infinite. Well, let me expand a little bit more on that. Then we did the binomial theorem. The binomial theorem allowed us to take a binomial, a term that looked like this. 1 plus x to the n, and expand that as an infinite series or a polynomial series or a power series. But this was the only type of function you could do that with. The binomial theorem did that. You were able to expand that binomial, especially when n was not a positive integer. The series expansion indeed was an infinite series expansion. So that's what the binomial theorem allowed you to do. Maclaurin's theorem or Maclaurin series expansion allows you to expand many other functions other than a binomial. For example, a little later on, you're going to see I'm asking you to expand these functions: the exponential function, the trig function, sine x, tan x, ln of 1 plus x, and so on and so forth. So it appears as if the Maclaurin series or the Maclaurin theorem helps us to expand many more, a whole host of other functions other than a binomial. Later on, you're going to see Taylor series expansion when we do that. Allows us to even expand even more functions. Gives us a greater latitude in the scope of type of functions that we're allowed to expand. So it's like they're all building on themselves. The binomial theorem allows us to expand only binomials as a power series. Maclaurin's theorem allows us to expand many more functions. And Taylor series even increases that range even more. All right, so what's the mathematical expression for that power series? Well, it's showing up right here. This is a quotable expression. We don't have to prove it. It can be proven, but I'm not going to prove it in this video. F of x, any function f of x can be expressed as an infinite sum. The sum from r equals 0 to infinity of f r primes of 0 over r factorial times x to the power r. I have to take a minute. I'll be right back. Okay, I'm back. Yes. Any function, the functions that you can actually expand, f of x, can be expressed as an infinite sum from r equals 0 to infinity of f r primes. That r that looks like a superscript on the f, that's r primes. I'll explain that in a minute. F r primes of 0 divided by r factorial times x to the power r. If you were to expand that out, starting by substituting r equals 0 into that general term, you'll get f0 primes of 0. And by the way, the prime is referring to differentiation. So if I have f0 primes of 0, that means it's a function itself. I don't differentiate at all, but I evaluate the function at 0. Divided by 0 factorial plus f prime of 0, that means you differentiate the function once and then evaluate it at x equals 0. Divided by 1 factorial times x, f double prime of 0 over 2 factorial times x squared. Double prime obviously means you differentiate twice. And so on down the line. Triple prime, differentiate 3 times. Quadruple prime, quintuple prime. Now, when the number of primes start to get too large, you just write it as an integer. So like this last one, for example, instead of writing f f prime 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 of 0 over 5 factorial times x to the fifth, it's okay to write f 5 primes of 0 over 5 factorial times x to the fifth. It's okay to do that. If you have to differentiate 7 times, you're going to write 7 primes. I wouldn't, anyway. And that series expansion goes all the way to infinity. Okay, the above is called the Maclaurin series expansion of the function f of x. The Maclaurin theorem basically says that the Maclaurin series expansion only exists for a function f of x if f of x and all of its derivatives can be evaluated at x equals 0. That is, if fr primes of 0 can be evaluated. Let me dig into that a little more. If a function is discontinuous at x equals 0, it implies that the Maclaurin series expansion does not exist for that function. So let's look at two examples. F of x is equal to 1 upon x. Well, the Maclaurin series expansion does not exist for that. If you look at the graph, you'll clearly see that the function does not exist at x equals 0. Right there, when x is equal to 0, the function is undefined. Same thing for ln x. When x is equal to 0, the function is undefined. So neither 1 upon x or ln x has a Maclaurin series expansion. Ln x, by the way, later on you'll see has a Taylor series expansion. All right. So unless you can evaluate the function at x equals 0, and unless you can evaluate all the derivatives of the function at x equals 0, the Maclaurin series expansion for that function does not exist. Okay. Let's keep going. The series expansion is only useful if it converges back to f of x. That is, for some function f of x, the limit as n approaches infinity of that infinite of the sum from r equals 0 to n of fr primes of 0 over r factorial times x to the r, that limit as n approaches infinity of that sum gives you back f of x. For all values of x, which are members of the set of real numbers. This is for some functions. For other functions, for other f of x's, the limit as n approaches infinity of that sum from r equals 0 to n of fr primes of 0 over r factorial times x to the r will give you back f of x for a limited set of values of x. And once the series converges, it can be used to find approximations. Let's compare that again with the binomial theorem. You would remember in the binomial theorem, when n was a positive integer, the series expansion was valid for all real values of x. And when n was not a positive integer, the series expansion was only valid for a limited set of values of x. Yes, remember that? Okay. Well, it's the same thing for the Maclaurin series expansion. Some functions converge for x being any value in the real number set, whereas some only converge for a limited set of values of x. All right, with that background, and basically you got to get accustomed to using this expression. All right, learn it well. Let's jump in and see if we can find the Maclaurin next series expansion for some functions here. I have a list. I'm going to go through all of them in this video. Use Maclaurin's theorem to find the power series expansion for each of the following, up to and including the term indicated. So, in the first case, they want the Maclaurin series expansion for f of x is equal to e to the x. And they want the series expansion for up to and including the term in x to the fifth. So the first thing I would usually do is to write that summation from r equals 0 to infinity of fr primes of 0 over r factorial times x to the power r. And then I would expand it up to the term that I'm interested in. I'm interested in the term up to and including the term in x to the fifth. So therefore, I'll write f0 primes of 0 over 0 factorial times x to the 0, which would be 1, plus f prime of 0 over 1 factorial times x, plus f double prime of 0 over 2 factorial times x squared, f triple prime of 0 over 3 factorial times x cubed, plus f quadruple prime, 1, 2, 3, 4 primes of 0 over 4 factorial times x to the fourth, plus f 5 primes, 1, 2, 3, 4, 5, of 0 over 5 factorial times x to the fifth, and so on. So it means that I have to differentiate the function 5 times. And in each case, I have to evaluate the function at x equals 0. Well, this is not a very difficult function to differentiate. Everybody knows that. If f of x is e to the x, f prime of x is also e to the x, f double prime of x is also e to the x, f triple prime of x is also e to the x, f quadruple prime of x is e to the x, and f 5 primes of x is e to the x, which makes, and now I have to evaluate the function and all of its derivatives at x equals 0. So the first one will say f of 0. By the way, this would be the 0 primes one. You don't necessarily have to write that 0 in there, but for completeness sake, if you want, you can do it. F 0 primes of 0 is e to the 0, which is 1. F prime of 0, e to the 0, 1. F double prime of 0, e to the 0, 1. F triple prime of 0, e to the 0, 1. F quadruple prime of 0, e to the 0, which is 1. And f 5 primes of 0 is e to the 0, which is also 1. And then I will simply substitute each of those values into the expansion that I have there. F of x, which is e to the x, can now be written as f0 primes of 0 is 1. 1 upon 0 factorial, that's also 1. Plus f prime is 1. 1 over 1 factorial, that's 1 times x. F double prime, that's 1. So this is 1 upon 2 factorial times x squared. F triple prime is 1. 1 upon 3 factorial times x cubed. The next one, 1 upon 4 factorial times x to the fourth, plus 1 upon 5 factorial times x to the fifth, and so on. This particular series expansion is valid for all real values of x. Again, you're not responsible for knowing which ones are and which ones are not. If you look at most books at this level, they will tell you the work required to know which ones are valid for all real values of x as opposed to which ones are only valid for a limited set of values of x is beyond the scope of this text. So at this level, you're not required to know how to get the range of values of x for which this series expansion is valid. They're going to tell you. And in fact, later on, as you'll see here, let me see if I can find it right now. You'll see there is a standard table, and it actually tells you which ones are valid for all real values of x. Look, e to the x, the one on top, that's the one I just did. It's valid for all real values of x, and so on and so forth. But I'm just getting ahead of the game there a little bit. All right. So that's the first one. Let's try a couple more. I'm going to go through all the ones in that sin x, tan x, b, f of x is sin x. And I'm supposed to go all the way up to x to the fifth, tan x up to x to the third, up to x to the fifth, tan x up to x to the third. That's the next one. E to the x times cos x up to x to the fifth. e to the x cos x up to x to the fifth. And what's the other one after that? 1 plus x to the n. Up to, I don't know what they said, x to the fifth or x to the fourth? X to the fourth. All right, so let's go down the line. I'm supposed to go up to x to the fifth here again. I think I can get x to the fifth. I'll show you why I said I think. So I'll write f of x in general is the infinite sum from r equals 0 to infinity of f r primes of 0 over r factorial times x to the r. And then I write out the series expansion. Okay, I'm not going to keep writing this out every time. So we can make it all fit in one line. And that's equal to f0 primes of 0 over 0 factorial plus f prime of 0 over 1 factorial times x, f double prime of 0 over 2 factorial times x squared, f triple prime of 0 over 3 factorial times x cubed, f 4 primes of 0, quadruple prime of 0, over 4 factorial times x to the fourth, and f quintuple prime of 0 over 5 factorial times x to the fifth. So that means I have to differentiate sine x 5 times. F of x is sine x. F prime of x, we know that to be cos x. F double prime of x is minus sine x. F triple prime of x will be minus cos x. F 4 primes of x would be, when you differentiate minus cos, you get positive sine. And F 5 primes of x is cos x. Yes, I can get up to that. And now I have to evaluate each one of these at 0. So, f of 0 is sine of 0, which is 0. F prime of 0 is cos of 0, which is 1. F double prime of 0 is minus the sine of 0, which is 0. F triple prime of 0 is minus the cos of 0, which is minus 1. That's triple prime, right? 0, 1, 0, minus 1. F 4 primes of 0 is sine of 0, which is 0. And F 5 primes of 0 is cos of 0, which is 1. So you can clearly see the terms with f of 0, f double prime of 0, and f quadruple prime of 0, those will all go to 0. So I don't even have to worry about those terms. Therefore, if I substitute into the series expansion, f of x, which is sine x, will give me f of 0, that gone to 0. F prime is 1, so that's 1 upon 1 factorial times x. F double prime went to 0. F triple prime is minus 1 upon 3 factorial times x cubed. X quadruple prime, that went to 0. And x quintuple prime, that is 1. So that's plus 1 upon 5 factorial times x to the fifth. So it appears as if this guy only has, this sine function only has odd powers of x, which is pretty cool. This series expansion is also valid for x, for all x. Valid for all, can't write anymore. for all values of x which are members of the set of real numbers, like so. And if you look at the standard, hopefully I did get the same thing. Sin x, yes, x minus x cubed upon 3 factorial plus x to the 5th upon 5 factorial. And so on. Okay, let's try the next one. Tan x. And I'm supposed to go up to x to the 3rd power. F of x is equal to tan x. So if I were to write out the series expansion, that would be this guy here, which I refuse to rewrite. I'll just copy and paste. There. There. Insert here. Paste. Voila. I shall not rewrite you if I don't have to. There. All right. So f of x is that up to determine x cubed plus dot dot dot. That the ellipses at the end simply shows that the series continues, but I'm not interested in the terms after that. I'm only interested in up to x cubed, which means I have to differentiate tan x 3 times. So let's see how that's going to go. F of x is tan x. F prime of x is sec squared x, which is sec x all squared. F double prime of x is 2 times sec x. I don't think I need to explain in any more detail how to do this. Y'all should be experts at differentiation, all parts of the calculus. 2 times sec x to the power 1. And when you differentiate sec x, you get sec x times tan x. This ends up being what? 2 sec squared x times tan x. Like so. And now I need one more derivative, f triple prime. Obviously this is going to be product rule here. I'll leave the 2 outside, so this would be 2 into, hold the second one fixed, tan x, differentiate the first. When you differentiate sec squared, you will get 2 sec squared x times tan x. I just did it above there. Plus, hold the first one fixed, sec squared x, differentiate tan, you get sec squared again. You tidy that up a little bit. F triple prime of x is equal to 2 into, on the inside you get 2 sec squared tan squared plus another sec squared, 2 sec squared tan squared plus sec to the 4th power x, like so. All right, so let's evaluate each one. F of 0 is tan of 0, which is 0. F prime of 0 is sec squared of 0. Now remember, sec is 1 upon cos. So that's 1 upon cos squared of 0. Cos of 0 is 1, so that's 1. F double prime of x, F double prime of 0, well, that would be 0 because the tan would be 0. And triple prime, this part will go to 0 because of the tan. So this ends up being 2f triple prime of 0 is 2 times 1 upon cos to the 4th power of 0, which I just think is 2 times 1 or 2. So the numbers are 0, 1, 0, 2. So let's plug in. I'll double check my numbers anyway. I know y'all do a good job. If I have any errors in there, you'll find them. F of x is equal to tan x. And when I get the series expansion, it is the first one, f of 0 is 0, so this one disappears. F prime of 0 is 1. 1 upon 1 factor is 1 times x. F double prime is 0. Yes, so this disappears as well. And then f triple prime is 2. So this would be plus 2 upon 3 factorial. 3 factorial is 6. 2 upon 3 is 1/3. So plus 1/3 times x cubed plus yada yada yada. So that looks like the appropriate one for tan x. I don't think I made an error, but again, y'all can double check me there. Okay, let's move on to the next one. F of x is equal to e to the x times cos x. That's a lot of differentiation there, man. F of x is e to the x times cos x. Lots of product rule involved there. All right, up to x to the 5th. So I'll simply copy this whole thing. Copy and paste. Who wants to write that back every time? Not me. There. Copy. Paste. Voila. Good. That's the f of x function right there. What are you doing? You're getting too bright now. Cancel that. Don't want to do anything with that. Ooh. Now it's stuck. All right, so let's keep going. I need to differentiate this function 5 times. Here we go. F of x is equal to e to the x times cos x. F prime of x is equal to hold the second one fixed. Differentiate the first plus hold the first one fixed. Differentiate the second. If I tidy that up, that will be e to the x into what's left there, cos x minus sin x. That looks decent, I think. Double check. Cos times e to the x. E to the x, differentiate the cos, you get minus sin. Yeah, that looks good. F double prime of x. Hold the second one fixed. Cos x minus sin x times the first. Plus hold the first one fixed. Differentiate the second. If I differentiate the second, I will get minus cos x. When I differentiate minus sine, we still get minus cos. Oh, what did I do? I really messed up. Differentiate cos, you get minus sine. And differentiate minus sine, you get, well, the minus, and differentiate sine, you get cos. All right, let me tidy this up a bit. This would be, if I factor the e to the x on the outside, what's left on the inside? It will be cos x minus cos x, that would disappear. And minus sin x would be minus 2 sin x. I think I'm right. So I'll write this as minus 2 e to the x times sin x. Always a good idea to double check your work. So I'll double check this. Hold the second one fixed, cos x minus sin x times e to the x. Differentiate the first, hold the first one fixed. Differentiate cos, you get minus sin. Differentiate minus sin, you get minus cos. The cos and the minus cos will disappear. Minus sin is minus 2 sin. Looks good. Let's go again. F triple prime is equal to, I'll put the minus 2 on the outside. And this is my product, e to the x and sin x. So hold the second one fixed. Differentiate the first. Plus hold the first one fixed. Differentiate the second. Cos x, which ends up being minus 2 e to the x into sin x plus cos x. Looks good, no harm double checking. Minus 2 into, hold the first one fixed, differentiate e to the x, get back e to the x, hold this first one fixed, e to the x, differentiate sin, you get cos. The only thing you factor is e to the x, it looks good. Sin x plus cos x. Alright, 2 more to go. F4 primes of x. Again, I'll put the minus 2 on the outside. Should I? Yeah, put the minus 2 on the outside. Hold the first one, hold the second one fixed. Sin x plus cos x. Differentiate the first. E to the x. Plus, hold the first one fixed. Differentiate the second. When you differentiate the second, differentiate the sin, you get cos. And differentiate cos, you get minus sin. Alright, let's tidy it up a little bit more. 4 primes. Now factor out, clean out from that, the e to the x comes out. So this is minus 2 e to the x. What's left inside my brackets? Sin x and then minus sin x will cancel out. Cos x plus cos x is 2 cos x. So what do I end up with here? Minus 4 e to the x times cos x. It's not so bad. That's assuming my my calculus there is good. What's wrong with this thing? Okay. Minus 2 e to the x. Cos plus cos is 2 cos. Sin minus sin is 0. All right, one more. F5 primes of x is equal to minus 4 into what you get when you differentiate e to the x cos x. And I remember differentiating e to the x cos x at the very beginning. And it gave me e to the x. Actually, I'll do it over. Minus 4 into, hold the second one fixed, cos x, differentiate the first, plus hold the first one fixed, differentiate the second, minus sin. If I factor out the e to the x, I end up with minus 4 e to the x into cos x minus sin x. Alright, that's all the differentiation. Now the only thing left to do is to plug in 0 everywhere. Let me change the red so that I can easily recognize this. So the first one, f of 0, e to the 0 is 1. Cos of 0 is also 1, so that's 1. Good. F prime of 0. F prime of 0, e to the x is 1. Cos x is 1, but sin x is 0. 1 times 1 is 1. So far, so good. F double prime minus 2 e to the x times sine x. Sine of 0 is 0. So f double prime of 0 gives me 0. So that one disappears. Wait a minute, I messed up. No. I'm in the wrong line. Take that out. It was simplified in the next line. F double, ooh. I think I have the right thing. Yeah, man. Bro, wrong with you. F double prime of 0 is 0. The next line is F triple prime. F triple prime is equal to minus 2, come across, minus 2 times 1, and inside the bracket is 0 plus 1, which is 1. So this all gives me minus 2. F quadruple prime started here and ended up here, right? This would be F 4 primes of 0 is minus 4 times 1 times 1, which is minus 4. Which is minus 4. And the last one, 4 primes, F5 primes is minus 4 times 1 again. F 1, 2, 3, 4, 5 primes of 0 is minus 4 times 1. Wow, minus 4. Anyway, let's see what happens. I think I'm right. Now I'm going to plug all those numbers into the expansion. I'm noted for making silly errors, but let's see. F of x, which is e to the x cos x, f of x, e to the x times cos x, that's equal to, all right, so let's start from the beginning. F 0 primes, or f of 0, that's 1, or 0 factorial, so all that's 1, plus f prime, that was also 1. 1 upon 1 factorial is 1 times x, so that's x, plus f double prime. F double prime was 0. That's strange. Why is that the only one that disappeared? F double prime was 0. Okay, so this one disappears. That went to 0. F triple prime is minus 2. So that's minus 2 upon 3 factorial, which is minus 1/3. Minus a third. Minus 1/3 times x cubed. 4 primes over 4 factorial, that's minus 4. And everything else is minus. Anyway, let's see what happens. Minus 4 upon 4 factorial, the 4 will cancel, and I'm left with 3 factorial in the bottom, which is 3 to 6. Minus 1/6. X to the 4th. And then f quintuple primes, that's 5 factorial. 6 5 30. Minus 1 upon 30 times x to the 5th. E to the x is valid for all real values of x. Cos x is valid for all real values of x. And I have a feeling that this expansion is valid for all values of x that are real. There's a way I can double check that using another method, which I will show probably in another video, or when we meet online, we'll look at it. But let's see. I think my differentiations are correct and my substitutions, but we'll see. All right, the last one is 1 plus x to the n. And I think that was supposed to go up to x to the fourth. X to the fourth. This one is an interesting one. Ooh, font size is huge. I see. What have I been doing? All right. I should expand this a little bit more on the corner there. All right, one more. I'm supposed to expand f of x is equal to 1 plus x to the n up to determine x to the fourth. So I'll write this one out just to get the feel for it again. Is the sum from r equals 0 to infinity of fr primes of 0 over r factorial times x to the r, which is f0 primes of 0 over 0 factorial, f prime of 0 over 1 factorial times x, f double prime of 0 over 2 factorial times x squared, f triple prime of 0 over 3 factorial times x cubed, plus f quadruple prime of 0 over 4 factorial times x to the fourth, plus the rest. Okay, so we got to differentiate this thing 4 times. F of x is equal to 1 plus x to the n. This looks like continuous use of the chain rule. F prime of x, you can't write to save your life, buddy. F prime of x is equal to n into 1 plus x to the n minus 1 times 1, which is just n times 1 plus x to the n minus 1. F double prime of x, drop the power again, n into n minus 1 times 1 plus x to the n minus 2. F triple prime of x will be n into n minus 1 into n minus 2 times 1 plus x to the n minus 3 times 1. And then the last derivative, quadruple prime of x, n into n minus 1 into n minus 2 into n minus 3 into 1 plus x to the n minus 4. And I'm supposed to evaluate each one of these at 0. F of 0 would be 1 to the n. I'm plugging in x equals 0. So it's 1 to the n of 1. F prime of 0, that would be n times 1, which is n. F double prime, n into n minus 1 times 1, which is n into n minus 1. F triple prime of 0, n into n minus 1 into n minus 2. And f quadruple prime of 0 is n into n minus 1 into n minus 2 into n minus 3. So if I plug those expressions into the f of x expression up there, f of x, which was 1 plus x to the power n, is equal to f0 primes of 0, which is 1, upon 0 factor, which is 1, plus f prime is n upon 1 factor is just n, so that's nx. F double prime is n into n minus 1, and then you divide that by 2 factorial times x squared, there, plus f triple prime is n into n minus 1 into n minus 2. I'm going to divide that by 3 factorial times x cubed, plus quadruple prime, n into n minus 1 into n minus 2 into n minus 3 upon 4 factorial times x to the fourth. Do you recognize this? This series expansion looks familiar? Well, you better, because this is the binomial theorem expansion the binomial series expansion. That's the binomial theorem right there. So effectively, the binomial theorem is like a special case of Maclaurin's theorem. The binomial theorem you get directly from Maclaurin's theorem when you find the Maclaurin series expansion for 1 plus x to the n. You end up with the expansion for the binomial theorem, that infinite series, when n is not a positive integer. All right, that's pretty cool. All right, what I'll do here, I mentioned it already, so but I'll mention it again. This guy right here, this table, is a standard table that they're gonna give to you. Right? It's part of that booklet that they usually give you when you're in the exam, writing the long paper. That is. And if you look at it, it has several of the series expansions that we just went through. It has a series expansion for e to the x. As for ln of 1 plus x, ln of 1 minus x. Note, it does not have the series expansion for ln of x because the Maclaurin series expansion for ln of x does not exist. I explained that earlier. If you cannot evaluate the function or any of its derivatives at x equals 0, there is no Maclaurin series expansion. All right, and then you have, of course, sine x, cos x, the general expansion that they have here. They didn't write the summation notation, but that's okay. And some other stuff at the below there. All right. I'm going to end this video here. I'll either do another video but let me explain what's to come. Sometimes instead of using Maclaurin's theorem to get this series expansion, sometimes the functions are a little more involved, and what you do, you try to use the standard table shown here together with the series expansion for each of the pieces to get the series expansion for what you want. So for example, one of the ones I just did above there, which was f of x is equal to e to the x times cos x. Remember that? Was it cos or sine? I think it was cos. Cos x, yes. Remember that? Okay, well, if I look up the standard tables for the expansion for e to the x and expand that up to however far they want, and look up the standard tables for the expansion for cos x, and then multiply those two series expansions, I should end up with the same thing I got when I used Maclaurin's theorem. So that would be a good check to see if all my differentiation up here was correct. So I'll leave that for another video or for when we meet directly online. All right, I'm going to stop this video here and we're going to continue at another time. All right, I'm out.